Right, thanks everybody for coming. This is University of California, Santa Barbara, lots of ocean, and KITP is at this corner here. If you come visit, try to take you sailing. That's not my boat, that's one of the beautiful boats. I don't have a boat, but I crew on a very slow boat. We say it maximizes the time on the water during races. So I'd just like to tell you a story about some, I think, interesting physical processes that play a role in a particular developmental biology system. This is work out of Sebastian Streichhorn's lab at UCSB, and the bulk of the work was done by Dylan Sislow, who was a graduate student of Sebastian's, and Boris Schraman, and he's now at Rockefeller working with Eric Sidger. And it's published here, and it's about this millimeter-sized organism. It's a shrimp, parhyale hawaiiensis, and during development develops some interesting orders of the cells. And looking at this kind of thing, this is how I got involved. An undergraduate working on this project came to show me this, and looks like a nice square lattice, but well, we knew it couldn't really be crystalline. And these kinds of things can have very subtle order. For example, if you look at the majority of pictures of crystals, or many pictures of crystals in the Cattell's solid state physics book, they're not crystals, but they're something a little different, which we'll talk about. And there's the cells dividing and reorienting. This is the organism. It's sometimes known as the Swiss army knife of small organisms like this. It has 17 different appendages. So all the way down like this, organized like this, going from the head to the tail. And those appendages do everything: feeling, walking, eating, sex, everything. And it's what's called a direct developer. So the small is the same as the large. There are no stages of development, and no larval stages, anything like that. This imaging for this work was done, as I said, in the Streichhorn lab with light sheet microscopy. So that's a very beautiful way of imaging, because you illuminate with a whole sheet of light, not a point like confocal microscopy, and you image orthogonally to the light. So it gives you, it's quite fast. It's one of the biggest advantages, and that's his actual lab, and you can see lasers and so on. I like to go in just so I know that it's hard to trust all the experimental results when you see how they're actually done. No. So this is some images from the light sheet microscopy. It has a lot of structure across many stages. And one would like to understand, it has a kind of a rectangular seeming body plan, and one would like to understand what are the recipes, how you can create such a body plan which leads to all the subsequent structure of the organism. This is also another direct developer, the homunculus from the 16th century of humans. So how do you go from this to this kind of structure? You know, those are the big problems in developmental biology, morphogenesis. Well, there's some kind of easy recipes for the system. How do you generate complex shapes in a system that will be out of thermal equilibrium, although some equilibrium ideas might be useful. These appendages are sort of genetically controlled, and if you have a mutant can make a leg where there should be antenna and so on. But still, and these are the segments with the 17 appendages reflected across this axis. It's the same. And how could you sort of develop this kind of order so you have a beginning plan? That's the question. This shows a little more in detail the segments. And each segment gives rise to one appendage in the development. You see here it's a little more developed, a little less developed. So what I would like to argue is that equilibrium condensed matter physics gives you a notion of a phase that can be very useful in biological systems. If you start with something that's completely fluid, then it's too disordered and it's too fragile. But you need flexibility. If you start with something crystalline, nicely ordered, but it's just too rigid, it's only going to produce dead things and not very interesting things in general, at least in biology. So is there something in between? I call it a structured fluid, something that has the flexibility of a fluid, but some kind of rigidity. And we know in equilibrium condensed matter physics such a phase for two-dimensional systems, and that's a phase, it's called orientationally ordered phase. An exact name for it depends on the degree of order. If it's six-fold order, which is most common, it's called hexatic. We will discuss for this particular organism something that develops a four-fold order, hence it looked a little bit like a square lattice. So such a phase is a fluid in the sense if you just looked at the centers of mass of everything, it would be translationally disordered, be indistinguishable from like a random gas or liquid. But if you look at how things are oriented, say from one point to the nearest neighbor point, you look at that orientation, just lines like we discussed earlier for liquid crystals, and then you look at how that's correlated with an orientation some distance away, then there's some kind of order in those orientations. And so it's an orientation that gives rise by breaking, in some sense, rotational symmetries, but not translational symmetries. In two dimensions, you can do that independently. You can first break rotational symmetries to develop this kind of orientational order, and then without breaking translation symmetries. And then you can subsequently break both and go into a true liquid phase. It's a little harder to do in three dimensions. I'm not even sure you can do it, because if you're in three dimensions, you have some orientational order, and then you can move around, look at it anywhere, it's going to change and wiggle all over the place. So much, much harder, maybe impossible to do in three dimensions. What are the order parameters for these phases? They're well known in equilibrium physics. The order parameter is just the sum from a given vertex, node, point, say the center of a cell, the nucleus or whatever, to its nearest neighbor. You measure the angle from I to j with respect to some fixed axis, so the ij vector compared to some fixed axis, and you sum up the phases. So if it's disordered, these all sum up random phases to 0. But if there's some orientation in order and orientation, this can be non-zero. Even more important really is correlation function between a local order here at point R and the local order, this orientational order at point 0. So 2 points distance R away, because that will really tell you if they know about each other. And then the really difficult thing for this kind of phase, because they're subtle, is that you also have to simultaneously establish that it's translationally disordered. Okay? So if you look at a density correlation function, that has to decay exponentially. And the reason this is important is there's orientational order in a crystal, obviously. In fact, a crystal has truly long-range orientational order. If you really want to establish something as a crystal, you should look at its orientational order. So to be in this intermediate phase, you have to establish both things, translational disorder and orientational order. Yes, Sananya?
If you just look at the orientational correlation, and that decays logarithmically, which
Power law.
can tell you that there's no translation order.
Yes, but it's very good to also check translational order. It gives you really, particularly if you don't have many decades, like, yeah. It's power law in this phase. I'll show that in a minute. Now, the transitions between these phases are Kosterlitz-Thouless-like or superfluid-like. Namely, they're driven by the analog of vortices for crystalline or for two-dimensional fluid systems. And here is shown this ordering, the symmetry breaking direction, or the disordering direction heating up. The basic defect in this system is the analog of the vortex is what's called a disclination, coming from disinclination. And it's a point, imagine you have the order of a crystal where everything's triangularly packed, or hexagonal lattice. It corresponds to a point that's not six-fold correlated, but five-fold correlated, losing 60-degree wedge. I just call that D plus instead of 5. And then the sort of anti-disclination analog is something that is one higher coordination number than the preferred 6. So it will be seven-fold coordinated thing, or a heptagon in the dual lattice. Now, so these things can roam around in principle like vortices. Now, if you go in this direction, I prefer going in this direction because the biological things should be pretty fluid in some sense. This intermediate phase, where you just develop orientational order, involves a binding of these two vortices. And I'll say how these objects break symmetries on the next slide. They bind, they're always in bound states, so they cancel each other out as vortices, vortex, anti-vortex pairs, but there's a free gas of these vortex-anti-vortex pairs. Now, this is a topological defect. I'll show you why in a minute, or remind you why. This is another topological defect, a distinct topological defect, very, very well known in Paris, due to work of Jacques Friedel and many, many others, called a dislocation, and I'll show you why that is a defect in a minute. And if you go to a crystal, these strongly bind, so you have a dislocation, and it's anti-dislocation that cancel each other out as defects, and you can think that this crystalline lattice has no defects, or just very, very tightly bound pairs of dislocations. So it's possible in two dimensions to cool and go through this phase, or to heat up and go through these two phases with the Kosterlitz-Thouless-like or close to it transitions between each one. The disclination was first discovered by Volterra, 1907. And let's put in here a pentagon corresponding to a vertex in the middle. That's five-fold coordinated. And let's look at a tangent vector to an edge and rotate around. So we rotate around. If we think we're in an ordered phase, we would think we'd turn 60 degrees. But there's a mismatch on the pentagon of 12 degrees. And you go around, adds up 24, 36, 48, 72. And it comes back by a vector that's displaced by 60 degrees. So that 60 degrees has been wedged out and glued up in the system with this kind of defect. So this means when you're here, you don't really know if you're pointing here or here. You just go around and then you come back and you're oriented over there. So they're basically equivalent or indistinguishable on the lattice. So that's the rotational, see these are rotations. That's the rotational defect that breaks the rotation, that breaks, if you have a gas of these, which is the the liquid phase, that breaks rotational symmetries because of that frustration, that ambiguity. If you go to bind two of these together so that that 60-degree turn from one and the 60-degree turn in the opposite direction from the 7 cancel each other out. If you go around and look at rotations around this pair, you have this other kind of defect, the dislocation-like defect. And this is an illustration of a dislocation in an actual experiment from William Irvin, who I worked with some time ago when he was at NYU. And these are actual colloids on a 2D surface, in this case flat, and there's a dislocation here. And if the best way to find dislocations is to look in the plane, if you look on your monitor, you look in the plane of the crystal and look at some Bragg rows. Some Bragg rows are nice. Some Bragg rows come in, and 2 goes to 1. If you follow on here, you look in the plane, you'll see a bifurcation. 1 row goes to 2. So 1 is like freely terminated. So it's a missing half line of Bragg rows. Because of the symmetry of a triangular lattice, there are actually 2 on a triangular lattice. There's a second line here that's freely terminating. And now let's look at a circuit going around a dislocation. Here's one on the clean part of, regular part of the lattice, and you make 6 steps around by, say, 3 lattice spacings here, and you come back to yourself. You do the same thing on a dislocation. You come back shifted by 1 lattice spacing, 1 edge. So that means you don't know if you're here or there. You think you're here, you go around once, and you end up here. So that frustrates the translational order of the system. So a gas of these guys will destroy the translational order, but preserve the rotational order, because the 5 and 7 cancels out with respect to rotations. We were talking about fourfold order in the case of this shrimp, and dislocation looks a little different on a square lattice, but here's the freely terminating Bragg row. So you see here the bifurcation looking along here. 3 goes to 2. That 3 minus 2 is 1 as the defines the degree, strength of the dislocation defect. And you can write this actually as a 5 and a 3 if you want to see something analogous to the 5 and 7, plus 1 above 4 and minus 1 below 4, the natural fourfold order of a square. Okay, so these are the things that Ananya was asking about, the important behavior you have to check. In the liquid, you have short-range translational order, short-range orientational order, exponentially decaying. In this hexatic, you have long range, you have orientational order, but in 2D, it's not, it doesn't have a non-zero order parameter. It decays as a power law. This is what's known as quasi-long range order. But the translational order falls exponentially. Short range, quasi-long range is the best you can do for orientational order in 2 dimensions. For the crystal, again, it's the crystal translational order is the analog of this one here. In 2D, it's power law, not truly long range because of 2D fluctuations. And the orientational order, here's what I was saying before, is truly long range for a crystal. Okay, so here's going back to parhyale. These are these light sheet images. And you see this is where I got involved. You see this kind of very regular looking order. This is head, this is tail, this is stomach, and this is dorsal behind it. And across here, you see pretty regularly ordering rows. And it's disordered here, and it's recruiting cells from this end, from the posterior end, onto this ordered region. So the question is, my question was, what kind of order do you actually have here, if any? That's a bigger picture. Looks like pretty nice, like four-fold kind of order. These are all cells. These are imaged from their nuclei. There's some membrane imaging as well. And there's 20 microns across. Again, this is a like whole 3D picture of this embryo. And this is an AP line going from head to tail, purple here. It shows ordering up here, disordering down here, and then growing over a span of 30 hours. So this data is collected 3 days after egg lay over a period of something like 35 hours. So it starts 3 days after. You can blow this up. Looks quite nice. The order is actually lower along this line here and more ordered on the sides.
So are there transitions between tetratic order and crystalline order or not?
Yeah, well, in this system?
In this system
no.
in general?
If it never crystallizes. It never crystallizes.
Never crystallizes.
Yeah, maybe if you put it in the fridge. If it does, those are probably thrown out of the lab, but no.
It's allowed to have a transition
yes.
between tetratic
Yes,
order
yes,
and
yes, yes. That would be the solidifying part of Costellet's thallus from hexatic to crystal.
No, from hexatic I know, but from tetratic.
Yes, they're all in the same universality class. All those p-fold orders are all isotropic to the superfluid phase. So I like to say this shrimp is not only a culinary delicacy, but it's superfluid as well. Yeah, all p-fold order is in the same universality class as a superfluid, and the exponent is also 1/4 for all of them. The p cancels out in the exponent at the transition, which is from the orientational order to the liquid.
So what do you mean by that? Eta 4 is equal to eta 6?
Yes, A to P, they're all the same. Now, the puzzle here, or important ingredient in all of this, is that there's cell division going on. It's not nearly as fast as Drosophila, but there's a lot of cell division going on. Well, its doubling time is like 10 hours. But the system is, not only consuming energy, active in that sense, but it's changing its number, particle number, cell division. And generally, that's a very disruptive process. Okay? And generally, this kind of environment would completely fluidize the tissue. So that's the first kind of puzzle. In that case, too fluid, it would just melt on the floor and you wouldn't produce anything interesting in structure. But here, I'll show you that these are just more images. And in order to look at the order, you use cartography. So you conformally map onto the plane from here to here, and then do a tessellation or a Voronoi decomposition. The conformal mapping is good because it preserves orientation, so it doesn't mess up any orientational order that might exist. It faithfully measures the orientational order. That's the kind of tessellation that you get. This is what Dylan Sislow did. Just for some intuition, these are what you can also look at, six-fold order in the same system. If you have a system that's sort of just for intuition, system that looks locally like this, like a cross, that's likely to have four-fold order. If you have a system like this with six-fold order, this will give 0 for this four-fold order parameter. And these are the angles and the lengths. You have to worry a little bit about the lengths of edges, but the exact order parameter here has some lengths put into it too, so you don't count very, very short edges. But they all give more or less the same result. So that's the measurement. And here again is just for intuition. Here's on the top left, is a system that has low fourfold order. This is just set up and measures 0.2. Goes between 0 and 1. Because of the structure you see is more like six-fold coordinated things. And if you plot orientations there, they look random. This one on the right has fourfold order 0.99, so maximum. And if you plot, and you can see, fourfold coordinations there. And if you plot the orientations down here, you see it's quite a line. They're lining up like a liquid crystal. This is an analog of a liquid crystalline phase, except you don't have the beautiful thing about these systems is you don't put in any microscopic structure that's anisotropic. Well, the cells are not isotropic, but you don't have nematogens in the usual sense. You develop the rod-like behavior from the orientation of neighboring objects. And there isn't even a bond. It's just a connectivity.
So why do you need to weigh the exponentials by the length squared?
Yeah. So there are some tessellations. Quite a few of the objects in the tessellations have very short length. And so you can't tell it could be a square with corners cut off. And there's sort of in the noise. So you de-weight those with putting in a length squared there. We checked various things, but this is the least noisy one. It's hard to know if there's a very short edge or not, basically. Yeah. The standard one wouldn't have these length factors in it. That's the intuition. So here's the actual measurement. So this is the time after egg lay, and this is plotting this fourfold order parameter. Sixfold is also measured. I'll show you in a minute. And it grows over about 25 hours to a maximum. It's about 0.4. It's not huge, but it's definitely in an orientationally ordered phase. And then it starts to drop again. And here's sort of images of how it develops. So it first recruits one row. I'll show you that again. One row, it's called parasegment, which divides. One of the cells divides and grows a second one there, and then that propagates out. So you get two rows and so on, recruiting from here. Here's fit against a Powell law plot. Again, it's only about a decade, but Powell law decays with an exponent that fits pretty well 1/4, which is what you expect from the Kostelis, Thouless, Nelson, Helper, and Young theory of melting, which predicted 50 years ago this kind of phase. Here you've also plotted in blue. Blue is early, 17 hours, and then this is 30 hours and 36 hours. So you see it grows. This is the correlation function. So what is going on here? Curiously enough, when people tried to find the hexatic phase very early on for equilibrium condensed matter physics, it's difficult, very difficult, subtle phase. And if you do it for example, repulsive particles with a Leonard-Jones potential, then it exists, but in a density range of 1%, between density 1 and 1.01. Okay? So you really have to kind of fine-tune to see it in the equilibrium situation. But the people who did this, which is Bagchi, Hans Christian Andersen from Stanford, chemist, and Swope, in '96, they did something very interesting. If you want to move through the space of tessellations of a 2D surface, there are two basic moves. There's the flip move, which most of you probably know about, so-called T1 move. That only just takes one diagonal and flips it to another diagonal. Doesn't change number of triangles or basic objects. The second one is barycentric decomposition. So you insert a vertex in the middle of a triangle and then retriangulate. These are called Packner moves. That's T2. With those moves, you can ergodically move between any triangulation and any other triangulation. Now, adding a point is just like cell division. Cell division naturally adds stuff. It adds a vertex and edges to the system. So let's think of the cell division as doing this kind of move across the space of triangulations. And when these people found the hexatic phase, what they did was did a kind of a grand canonical simulation, but they started with n particles. The statistics are not very good in this subtle phase, not good enough to see power law. Then they added a particle and did a simulation with n plus 1 particles, and then back to n later. And they took these two ensembles and merged them to get better statistics to see the hexatic phase. So in fact, these guys were using they're using cell division or the T2 move on their statistical ensembles to see this subtle phase. And what I like to argue is the biological system is doing this naturally with cell division. Now, what happens if you go to material science, adding an object is called an interstitial. You can remove one that's a vacancy. You can add one particle to a kind of ordered array of atoms or anything else. And what happens is that an interstitial by itself is not really stable. It evolves through fluctuations to a dislocation pair, so 5, 7, 7 pi pair, a dislocation and anti-dislocation. Oh, I forgot to say that the mismatch when you translate around dislocation defect is a lattice spacing called the Burger's vector. If you have this dislocation and anti-dislocation pair, the Burger's vector cancels out. So an interstitial can, in fact, by fluctuations, become any complex of dislocations whose Burger's vectors sum to 0. And you'll see if you do experiments on colloids or simulations or anything else, you get usually 2 dislocation pairs or 3 in this kind of hexagonal structure. And in an ordered kind of system, these rattle around, but they never unbind. But if you take the system on curve space, or if you add noise, and the systems that we'll be talking about are both active and undergoing cell division, then these dislocations can unbind and roam around and stir up the system. And I'd like to argue that that process can enable you to find local minima corresponding to orientationally ordered phases. So I call it, it's a fancy name, just defect-driven morphogenesis. But that's the basic idea, and later I'll show you some ways of checking that idea in a different system. So here's one cell, this is fourfold, it divides, okay, you get these 2. This becomes some complex, dislocations, can explore, move around, and find the orientationally ordered phase. That's the idea. Here's a solid square lattice with Portuguese tiling. Okay, so yes,
Can I ask another question?
Yes, please.
Is there any local symmetries that forces tetratic order rather than hexatic order or triadic order? I mean, could you guess from the beginning that it would be tetratic or whatever?
Yes, we don't know.
We don't know.
So we have no idea about that. And there could be very early stages of like actomyosin cables, genetic processes, and so on that single out that first parasegment, that first row, with some kind of breaking symmetries. We have absolutely no idea here, and we would need, the imaging would need membrane dynamics to try to uncover something like that early on. But there's no, the cells themselves never have any a priori order for shape, order and shape.
And it's always tetratic tetratic, it cannot be hexatic in some cases or whatever?
Yes, this system is tetratic. Other systems could be hexatic. It's actually more common. Yeah. Yes, Ananya.
Is it known, at least in equilibrium, how the insertion or deletion of particles, so interstitials and vacancies, change the oscillates through the temperature for solidification?
Change what?
The KT transition temperature for solidification.
No, it should not change that.
It shouldn't change that,
No.
right?
No, that's not universal anyway,
Yeah,
actually. So
the real question was whether
So
it's pushed to zero or not.
yes, no,
Right.
yes. That is a good point, and I'm going to show you coming up with the numerical simulations of a different system that the crystalline order can be destroyed, generically destroyed, when it's active and dividing cells. Yes, absolutely. Any other questions on this part? Okay, so I wanted to understand this a little better, and so I teamed up with Max B, who is at Northeastern University, expert in simulating epithelial tissue dynamics and so on, and his student Yuen Tang at Northeastern. She's going to Singapore for a postdoc. And a UCSB undergraduate, Jessie Chen, who's now at NYU in graduate school, working with Paul Chaikin. So to check the combined role of activity, which will be motility in this case, and cell division, that's in this paper, we looked at the area perimeter vertex model with two important ingredients. So this is a model where the energy is given by a sum of two terms. One is quadratic in the area of a cell with respect to some target area, and the second term is the perimeter of a cell compared to some target perimeter. And the extra ingredient is that these cells will be self-propelled, like motile objects with some fixed velocity v, and there'll be cell division. So you randomly pick a cell, divide it in two, and then in this case, remove a cell somewhere else. So the total number is fixed. So there's no growth in total number of cells, but there is the process of cell division. This is a very rich system because A and P are nonlinearly connected. I mean, these two terms are connected, and the relation between A and P is an inequality. There's a lot of rich dynamics, and the self-propelledness is a rotation of this this axis there of the orientation of a center to one edge, moving around as a self-propelled like particle with stochastic noise. So what happens in this system? First of all, pitches. So this is now with a fixed division rate and varying cell motility. So you start here, we can start here, very high cell motility and cell division. You see you get a gas of these disclinations. So that corresponds to the liquid phase. In the middle here, this intermediate self-propelled velocity, 0.35, you see these red-blue pairs, that's a dislocation. You see the dislocations are isolated, highly non-trivial. This means up from here, the free disclinations are bound, but just bound into disclination pairs or the dislocation. So that is the characteristic of the orientationally ordered phase. In this case, it's six-fold ordered, not four-fold. The phases are isotropic in terms of their statistical behavior. And then as you go lower, something happens, but these dislocations can start to coalesce, and we'll come back to what this is in a minute. Yes?
I have the same question as before.
Okay.
Do you know what you could change to this model to make it tetratic and not hexatic or not?
You could, yeah.
How would you do it?
You have, okay, so you would just do a quadrangulation for your cells
Yes.
and make that self-propelled. And your basic object, instead of being a hexagon, would be a square.
But here you don't impose the shape of the cell at all.
Yeah, it starts with a tessellation, so it does. It starts with a hexagonal
Can't you change
decomposition.
the ratio?
Yes, yeah.
But then that will probably change it.
That can change, yeah. But this is the basic zero temperature setup. This one has a bias.
This one has a bias.
Yeah.
You don't you put the points randomly and do a Voronoi tessellation in the beginning?
Yes, no. I mean, it depends. If you start with a random state, yes. If you start with some ordered state, it's
You start with another state which is biased to it.
Yeah, you can. You can also start with a random state. This is an important point, which is related to what I was saying before. If you throw down a set of points and you triangulate, if you find order, it's almost always six-fold order. For example, electrons for a Wigner crystal, the energy of the triangular lattice or hexagonal lattice is a little bit lower than the energy of a square lattice. So generically, in these kind of tessellations of random things, even if you start with a random state, you'll get something with six-fold, if there's any order, six-fold order. Square lattice is peculiar because, for example, if the nearest neighbor distance is 1, the second one is square root of 2. That means if your microscopic potential has to have two minima, one at 1, one at square root of 2. Very unnatural, very fine-tuned. If you throw down disks and pack them maximally, they have 6 nearest neighbors, kissing number, and so on. So fourfold is unusual in nature and unusual in mathematics for packing kind of problems. Yeah, so that's another important ingredient. Of course, I would like to understand how the fourfold order comes about in this particular system, but it's not the most important thing. Yes?
Just a quick question.
Yes.
The relation between A0 and P0
Yeah.
also somehow tell you about the order?
Yes, yeah. Yes, so that ratio, which is called the shape index, S, is P0 over the square root of A0. So this number, this is where the interesting geometric inequalities come in, because this number can be arbitrarily large because you can take an object like this and make the area very small for a given perimeter. So you can always make this go to infinity, but you cannot make it arbitrarily small, because if you want to enclose a certain area, you need a certain non-zero perimeter. So this S is greater than or equal to some critical value, S star. And so here we will start with the phase that allows a solid realization. Yeah. If you start with something that's, So this is the isoperimetric inequality, and we'll be working in a range to begin with where that's satisfied. Yeah. In that case, without cell division, it's shown that you can get solid phases and fluid-like phases, rigidity transitions for these 2D models of tissue in this area perimeter model. And you do that by varying that shape index. Exactly. This shows the density of defects. So you see the density of dislocations is red here, and it goes it's non-zero in this region here, whereas disclinations go to 0 in this intermediate phase here, what I'm calling the hexatic phase. So there are no free disclinations like in the liquid, but there are free dislocations. Here's a plot of the orientational correlations as a function of time. There's the orientational correlation function, psi6r, psi60. This is the parallel behavior, and you can see as the system, this is for varying motilities. So there's too low a motility, you go up, there's a range of motilities, that intermediate phase, where you start to see this power law decay. Now, and these show susceptibilities that confirm transitions in this system here. There's structure factors characteristic of, this is the orientationally ordered phase or ecstatic phase in the middle here, liquid, crystal, Bragg, like scattering patterns. And then there's the phase diagram. So now the most interesting thing, this ecstatic phase was known by Chamara and Lee for a system without cell division. Okay? So if you have cell division, you can have crystal, ecstatic, liquid phases. What we found for the system with cell division and motility is that the crystalline phase is destabilized, is unstable. That's related to your question, Ananya. So you have this reentrant phase-like diagram. So for example, if you take this axis here, you're increasing motility. Yes, there's the range where it's ecstatic, and here's the range where it's liquid, easily understandable, high motility, this intermediate range where it's ecstatic, okay. But down here, low motility, it's liquid again, reentrant. This is interesting. Notice here though, this is for non-zero cell division. So cell division here is what happens is, oh, and you can go this way, okay, increasing the cell division rate. Very high cell division rate, you go liquid again. And in this range, you get ecstatic. Notice it's quite a big ecstatic region as compared to the equilibrium case. Now, what's going on here? How can, this is an order from disorder-like process. Let's look down here. The high motility and high cell division rate regions are easy to understand, highly disordered. Well, what's going on down here? What's going on down here is that basically one noise or another, I like to think of them as noises, the noise due to motility or the noise due to cell division. One noise or the other destabilizes the system and it becomes liquid. Now as you go up here, so here you have a gas of disclinations. As you go up here, even though you're increasing motility or activity, whatever you like to call it, this leads to a binding of the disclinations into free dislocations. That is peculiar, and that is what I believe is this defect-driven ordering, the formation of dislocations from cell division, exploring the whole phase space of the system, and allowing these disclinations to find a phase where they bind into dislocations. That's the picture. This is the ecstatic to liquid transition, and it matches where the susceptibilities diverge. And you can do more than that. You can look at how this is correlated, this transition line, for example. So first of all, way down here at zero division rate, you would have crystal phase. Okay? Yeah, that's what Chamara and Lee discovered. So then you would go crystal, ecstatic, liquid like an equilibrium. You can get some insight into this transition line here, ecstatic to liquid, by looking at the competition between cell division and cell rearrangements. There's cell division, then there's mechanical relaxation and rearrangements. So in this transition line actually matches where cell rearrangements, as you would measure in a glassy-like system or disordered system, match the cell division rates. So the two are working in competition in a very unusual way. You can, you can make a very, very crude mean field model of this process just by having, just making disclinations which can propagate fluctuate over barriers to bind to dislocations, the hexatic, and over another barrier to bind dislocation with anti-dislocation to a crystal, and put in gaps here and put in transition rates, and you get a phase diagram that's like this. This case, this is a very, very crude model, has the reentrant part, but it has a little crystalline piece in it too. So I don't know whether I trust that, but it gives a picture of how this could proceed by this kind of a competition that I've been talking about. So the conclusion is, first of all, such a phase is very beautiful in a biological system because it has the rigidity to deforming orientations. That's the superfluid-like rigidity. And it's one that's very flexible because the system is fluid. And it can generate body plans and structures which then lead to structure. The active forces from cell division or apoptosis can lead to a broad region of the parameter space for hexatic order. So somehow adding this cell division and motility, you go from a very tiny window of hexatic order to a broader thing through these kinds of non-equilibrium processes that enable you to reach this subtly ordered phase. So I think that's a generic mechanism that needs a lot more exploring. Simple mean field theory can explain this mechanism, but it's extremely crude. And yeah, I think this is an idea that can be a small piece of how developmental system makes a body plan. Okay, I'll finish there.